Section 8.1 is sequences. So we're going to start by doing kind of a review of sequences that you have looked at, hopefully back in pre-calculus. So defining a sequence. A sequence, A sub n, is a list of numbers written in explicit order. For example, the sequence A sub n is all of the terms A sub 1, A sub 2, A sub 3, all the way up to A sub n, or continuing on infinitely, where A sub 1 is the first term and A sub n is the nth term of the sequence. So if we let these terms together be a function, with the domain being the set of positive integers and the range being the sequence of terms, then if the domain is infinite, then the sequence is an infinite sequence. If the domain is finite, then the sequence is a finite sequence. If the domain is infinite, then the sequence is an infinite sequence. So some terminology of sequences that you should have seen before. So let's define a sequence explicitly. So the first four terms and the 100th term of the sequence A sub n, where the rule for A sub n is A sub n equals -1 to the nth over n squared plus 2. So setting n equal to 1, 2, 3, 4, and 100 will get us the first four terms and the 100th term. So A sub 1 is -1 to the first power, just substituting 1 for every n value, over 1 squared plus 2, which is -1/3. A sub 2, -1 squared over 2 squared plus 2. A sub 3, they didn't show the work, but it would be -1 cubed over 3 squared plus 2. A sub 4 would have been -1 to the 4th over 4 squared plus 2, and of course a to the 100th, following our rule, is -1 to the 100th over 100 squared plus 2, and that gives us this. Okay, and notice that since we use this -1 to the power, the terms alternate being positive and negative depending upon whether the power is odd or even. So that's an explicit rule. It's a rule that allows us to find any term by simply plugging in the value for n, which is our domain, our integers, into our function rule. Defining a sequence recursively. So when we define recursively, we define each term based on the term that came before it. So find the first three terms and the 7th term for the sequence defined recursively by the following conditions. The first term is 4. Every term thereafter is the previous term minus 2 for n being greater than or equal to 2. So I'm going to get rid of this and show you the work that is behind this. So let's look at this. B sub 1 equals 4. That's a given. B sub 2 is going to be, again, plugging 2 in for n, is going to be B sub 1, the previous term, minus 2, which would be, we already know B sub 1 is 4. B sub 3 would be the previous term minus 2. The previous term was 2. B sub 4 is the previous term minus 2. The previous term was 0. I'm going to shorten this a little bit by not writing this step. B sub 5 is the previous term minus 2, which is -4. B sub 6 is -4 minus 2. And B sub 7 is -6 minus 2. So it asks us for B sub 1, 2, 3, 4, and then the 7th term, but you notice that in order to get to the 7th term, I also have to find the 5th and the 6th. With a sequence that is defined recursively, I always have to know the term before to find the next term in the sequence. Okay, We'll look at two different kinds of sequences now, arithmetic and geometric. Some sequences are defined by a rule that is neither arithmetic nor geometric, but some of them can be defined in this special subcategory. So a sequence, A sub n, is arithmetic if it can be written in the form A plus D, A plus 2D, all the way up to A plus n minus 1D. You notice that A sub 1 doesn't have any D's added. A sub 2 has 1D. A sub 3 has 2 D's added to it. A sub n has A sub n minus 1 D. For some constant D, the number D is called the common difference. Each term in an arithmetic sequence can be obtained recursively from its preceding term by adding D. So this would be the recursive rule. A sub n is the previous term plus D. We'll also look at how to do an explicit rule for arithmetic. Okay, so defining an arithmetic sequence. So given the following sequence, we're going to start with -3, 1, 5, and 9. And that continues. We want to find several things. First, we want to find the common difference. What number is our common difference between each term? One way to find this is to take the second term minus the first and subtract. So 1 minus -3 is 4. 5 minus 1 is 4. 9 minus 5 is 4. You notice that 4 is the number that as I move forward each time, it's what I am adding to the previous term. So my common difference here is 4. The difference between each pair of terms is 4. Okay? Now we want to find an explicit rule. So my explicit rule, A sub n, for an arithmetic sequence is always A sub n equals the first term, in this case -3, plus n minus 1 times our common difference, which is 4. So this would be the explicit rule for this particular arithmetic expression. Let me write explicit rules in general terms. So the general explicit rule for any arithmetic series would be that A sub n equals A sub 1 plus n minus 1 times the common difference. So using my explicit rule, I could find, for example, A sub 9, which would be -3 plus 8 times 4, which would be 29. Right? Yes. Okay? C. Let's find a recursive rule. For a recursive rule, I have to first give the first term. In this case, A sub 1 is -3. And then I need to define every term after that by saying A sub n would be, what am I thinking here? A sub n minus 1, the previous term, plus our common difference 4. So this would be our recursive rule, and this would be for n greater than or equal to 2, because I already have done A sub 1 here. So again, if I wanted to find the ninth term here, I would have to start with A sub 1 equals -3. I would say A sub 2 equals -3 plus 4, which would be 1. A sub 3 would be 1 plus 4, which would be 5. A sub 4 would be 5 plus 4, which would be 9. And I would have to keep going. Those were the ones I already had. A sub 5, A sub 6, A sub 7, A sub 8, A sub 9. Each time I'm going to add 4. So 9 plus 4 is 13. 17, I'm adding 4 each time. 21, 25, 29. So my explicit rule makes it much easier to find large terms further down. My recursive rule allows me to find terms one after the other. Okay? So that's our arithmetic sequences. Let's look at geometric. Again, backtracking the arithmetic, every time we want to increase in our sequence, we add a certain number. For the geometric, it's going to be that we are going to multiply by a certain number. So we start with a sub 1. We take a value, multiply it by r to get our second term. We multiply it by r and multiply it by r again to get our third term. So when we are looking for our first term, it's just a. Our second term is a times r to the first. Our third term is a times r squared. Our nth term is a times r to the n minus 1, where r is a non-zero constant and r is called the common ratio. Each term in a geometric sequence can be obtained recursively from its preceding term by multiplying by r. So a sub n is the preceding term times another r. Okay, so let's do a couple of this. Let's take a sequence that is going to be 1, -3, 9, -27, etc. So to find, first of all, we want to find our common ratio. In other words, what do I multiply each term by to get the next? In this case, our common ratio is going to be 3. If you can't tell this, if you can't tell by just looking, -3, and saying, well, 1 times -3 is -3. If I multiply by -3 again, I get 9. You can find the common ratio by doing division. The term in front divided by the one before it. 9 divided by -3, -3 over 1, all of these equal -3. So that's my common ratio. All right, let's go ahead and find an explicit rule. And our explicit rules for geometric series says a sub n equals a sub 1 times r to the n minus 1. So for this particular geometric series, a sub n is going to be 1 times -3 to the n minus 1. Now, sometimes we take this and break it down, and that -3, we factor it so that we have 1, and I don't really need the 1 here, and then I take -1 to the n minus 1 times 3 to the n minus 1. When I see this, I know that my series, is going to flip-flop plus minus plus minus plus minus. So this notation of pulling that -1 out will become useful as we move forward. All right, let's find a recursive rule. Again, with the recursive rule, I need to know that a sub 1 equals 1, and then a sub n would equal 1 times our r value, which in this case is -3, to the, we're doing recursive. My bad. Recursive rule defines it based on the prior term, so a sub n will be a sub n minus 1 times our -3, or -3 a sub n minus 1. So the previous term times -3. Again, with the recursive rule, to find a certain term, I have to do every one preceding it. For the explicit rule, I can just plug in to find any term wherever I'd like. And this is for n greater than or equal to 2, because I've already defined a sub 1. Okay? All right. Constructing a sequence. What if I know the terms in the sequence, but I don't know the r value yet? So if I only know the second and fifth term of a geometric sequence, I can first of all work backwards to find some of the information I need. So the ratio of a sub 1 times r to the fourth, that's my fifth term, over a sub 1 times r, that's my second term, is negative 48 to 6. So simplifying, canceling, and using my power rule, and simplifying this, I get r cubed equals negative 8, so r is negative 2. That means that my common ratio is negative 2. Now remember, when I have an explicit rule, I need to have my a sub 1. So we know that a sub 1 times r will give me a sub 2. So a sub 1 times negative 2 has to give me negative 6. So therefore a sub 1 is 3. So now I can write my explicit rule, the first term times my ratio to the n minus 1, and again pulling out that negative 1 to the n minus 1 as a separate term indicating plus minus plus minus. Okay, limits. This would be new content. So when we talk about the limits of a sequence, let L be a real number. The sequence a sub n has limit L as n approaches infinity. If we can force a sub n, again n getting towards infinity, to be as close to L as we wish for all sufficiently large n. Same thing as a limit approach any other limit approaching infinity, that whatever our sequence is, and a sequence is a series of dots because it's in individual terms, if it's approaching a particular value, in this case 0, that is the limit. More formally, given any positive number epsilon, where epsilon is a small number, there's a positive number m, such that for all n greater than m, in other words, as we are getting very large, the difference between the limit and the nth term is always going to be less than this small number epsilon. We write the limit as n approaches infinity of a sub n equals L, and say that the sequence converges to L. Sequence that do not have a limit diverge. This is going to be really important vocabulary for us moving forward into our calculus look at sequences and series. All right. Properties of limits. You've seen these before. They are the same as they have always been. They apply to sequences just like they apply to any other limit. So take a look at this, copy them down if you need them. So let's find the limit of a sequence. Determine whether the sequence converges or diverges. If it converges, find its limit. So here is our sequence. We're going to use the limit as n approaches infinity of 2n minus 1 over n. They've broken this down into two pieces using properties. The limit as n approaches infinity of 2 is 2. The limit as n approaches infinity of 1 over n is 0. Therefore, the limit is 2. Since it has a limit, this converges. So again, a sequence with a limit as n approaches infinity is called a convergent series. The squeeze theorem. We're going to look at this a little bit. If the limit of a sub n is equal to the limit of c sub n, and they both have the same limit, so in other words, one sequence and a different sequence have the same limit, and if there's an integer n, large number, for which a sub n is always less than b sub n is always less than c sub n, in other words, if b sub n is always between these two, for all n's greater than this large number, then the limit as n approaches infinity of b sub n must also be L. So let's look at this. If I have a sequence A, and it is approaching a particular value, and I have a sequence C, and it's also approaching this particular value, and if B is always in between the two, then its limit must be the same as the limits of the other two functions. That's the squeeze theorem. The absolute value theorem. Consider any sequence a sub n if the limit as n approaches infinity of the absolute value of a sub n is 0, then the limit of the function a sub n is also 0. We will use this theorem as well. That is it for now.